Okay, so in the previous class, I had introduced a new topic called transformers. I hope you should be able to see the screen right now. So this topic is called transformers, and it is unit for single phase transformers. So, and I began by saying that transformer is an AC device which converts voltage and current levels from one circuit to the other circuit. So here in the diagram you can see input side voltage is less, on the output side current is 40 amperes and the voltage is 1000 volts. So you notice that voltage has increased from 100 to 1000, whereas current has decreased from 400 to 40. So in effect, the transformer is a device which converts voltage, and accordingly the same ratio the current also is reduced. So if voltage is increasing, current is reducing, so that the product power VI cos phi will remain same. So in this example, 100 volts into 400 amperes is 40 kilowatts, assuming power factor is 1. And the same on the other side, 1000 volts into 40 amperes is again 40 kilowatts. So this is one example of how a transformer works. Then we have this equation V1 by V2 is I2 by I1. The inverse relation applies. So V1 increases, that means I1 decreases, so and so on. So, or in other words, V1 I1 is V2 I2. And K is called as a transformer ratio, which is defined as V1 by V2. Now, if you further go, why we need a transformer? So, for transfer of power over large distances with least losses, we need a transformer. So, let's look at an example. So, we looked at an example where in the example, you have on the left side, there is a source, 200 volts. On the right side, there is a load of 100 volts. And the line resistance is 1 ohm. And 10 kilowatt load, we are assuming at unity power factor. So, because the load is 10 kilowatt and the voltage is 100 volts, so the current is 100 amperes. Now, this 100 amperes current will cause 100 volts of drop here, and also power loss will be 100 square into 1, that is 10 kilowatts. So ultimately, what is efficiency? Output by output plus losses, so which is nothing but 10 kilowatt by 10 plus 10 kilowatt. So only 50% efficiency we are having. So this is a very bad transmission of power, because 50% of the power is going into losses. Then in the case 2, I am introducing two transformers. At the sending end, I am using a step-up transformer. At the receiving end, I am using a step-down transformer. So what happens? So the voltage is stepped up, and then the current is reduced, and therefore power losses are reduced. And at the receiving end, again voltage is stepped down. And as far as load is concerned, load is exactly same. Here the load was 10 kilowatt load at 100 volts. Same 10 kilowatt load at 100 volts I am having. So this will take 100 amperes. But because it's a step down transformer, on the other side the current will go only 10 amperes. And because of 10 amperes current, there is only 10 volts of voltage drop, and power loss is only 100 watts. Now if I calculate the efficiency, I am getting 99% efficiency. So look at the efficiency increase. So just by stepping up the voltage, I am from 50% efficiency, I am getting 99% efficiency. So this is the importance of transformer. That is why we use transformers everywhere. So the efficiency was 50%. Now efficiency has become 90%. Let's continue. So now what is the working principle of transformer? How will a transformer able to achieve step up and step down? So for that, I have again shown this diagram. Here number of turns is 5. Here number of turns is 10. So when I apply the voltage, there is an initial current and a flux phi. This phi naught flux is inducing EMF E which is given as n d phi by dt. And if I simply substitute the sine omega t and everything, so I'm getting E1 and E2 in this form. So that E1 and E2 will be proportional to N1 by N2. So that is what we are able to prove here. Now what happens when I connect a load? So when I close the switch, a load is connected. So I2 will start flowing in the secondary because E2 voltage is there. I2 is the current and it is being consumed by the load. Now this current I2 in turn creates a flux phi2 that is opposing the main flux. So therefore the main flux gets weakened and therefore E1 gets reduced. And therefore V1 and E1, if you compare, V1 will be more, E1 will be less. So more current will be pushed into the primary winding. And the amount of current that will be pushed will be proportional to the turns ratio again. So that's why I mu is a no load current plus I2 dash is the equivalent primary current. The total is I1. Now this additional current I2 dash will create another flux phi1 which will cancel out phi2, restoring the original flux phi naught. So therefore in the transformer always the flux is same phi naught, and that is also one important point about this. Then further developing on this EMF equation, we have derived this very important EMF equation for a transformer, that is E1 is 4.44 into N1F into phi m, or 4.44 into N1F into B maximum into A. This is the maximum flux density and area of cross section. So based on that, we had solved a couple of problems also. So let me show you as an example that class. So that example. So I'll change the document. Be able to see the example problem on your screen. So this is example 12.1, and what is the given data? So given data, I'm having a one phase 40 kilovolt ampere 6600 by 500 volts 50 hertz transformer. So this is basically the definition or rating of the transformer. And maximum flux allowed in the core is 70 milliwebers. So you should be careful with the units when always this kind of problems are coming. Milliwebers means 10 power minus 3 you should consider. So now given this data, you have to find the number of turns in transformer. So E1 value I already know, 6600 is equal to 4.44. In the place of F I substitute 50, and in the place of maximum flux in the core I substitute 70 into 10 power minus 3, and only N1 is unknown. So when I solve it, I get 424.7 turns. So turns is basically an integer number. So you round it off to 425 turns in the primary. Similarly, the same thing I apply for secondary, and in the secondary winding, I am getting 33 turns for the problem. Next, let's look at quickly the one more example. So this is example 12.2. So let it open. So here I am having determined the rated current of transformer mentioned in example 12.1. So the rated current I want to find out. So how to find the rated current? You take the kVA rating and then divide by the voltage rating. So 40 kVA, so that's why 1000 VA divided by voltage. So I'm getting 6.06 amperes is the rated current in the primary. Whereas rated current in the secondary is 80 amperes because the voltage is only 500 volts. So this is very straightforward calculation. So this also, that is example 12-3. So let me just now you should be able to see that. Yeah. So the maximum flux density in the core is 1.5 Tesla, 250 by 2500 volts, 50 hertz transformer. Volts per turn is 9 volts. Determine number of turns. So again, everything is known. E1 is given, number of turns is not known, flux density is given, and A is given, F is given. So of course, number of volts per turn is given. So that's why we can say number of volts per turn is E1 by 9. So like this we'll get. So overall we are getting this N1 has to be 28 turns. So then based on that, I can find the cross-sectional area. Similarly, one more example we have solved, and finally the summary of last lecture is what is the transformer, why transformer is required, EMF equation of transformer, and some numerical examples we have solved. So this is about the first class on transformers. So today, so basically review. I want to review of one-phase AC circuits. So meanwhile, let me, before I go forward to doing this review, let me ask you whether you have any doubts based on the previous lecture. Anybody having any doubts, feel free to ask your doubts now. So I'll give you a couple of minutes time. You can ask your doubts. Secondary turns. So the purpose of steel core is so basically a doubt. So why core between primary and secondary? So the doubt is why we require a steel core or a core between the primary and secondary. So the answer is to avoid loss of flux. So the flux, there should be strong magnetic coupling. For EMF, for inducing EMF. See, the secondary coil is induced, EMF is induced in the secondary coil only because of the flux generated by the primary coil. So that is the reason why the core is required to carry all the flux from primary to the secondary. So that is the reason. So I hope that answers your question. So having a core will result in not losing the flux. Okay, so let me begin by doing a review of one-phase AC circuits. Why it is important? This is very important to be very strong in AC circuits to understand transformer, because once you are strong in AC circuits, the rest of the transformer subject is just application of your knowledge of AC circuits. Easily you can solve the AC circuits, that is the transformers. So let's begin by some example problems. So let's call this example 14.1. So the question is simple. So there is another question, what kind of core we have to use? So we have to use the core which can support high flux density. So core should be able to offer low reluctance and high flux density. So I am typing the answer, capable of high flux density. without saturation. So the answer I have given in the chat window. What kind of core we have to use? Core should be able to offer low reluctance to magnetic field and be capable of high flux density without saturation. So that is the requirement for the core. Okay, so let me continue now. The example one. Find current in following circuit. And draw vector diagram. So the circuit is like this. So basically it's a simple circuit with a resistance 10 ohms and inductance. Okay, so I'll give you 20 millihenries and capacitance is, let's say, 200 microfarads. And the supply voltage is 100 volts, 50 hertz. So what is the current in this particular circuit? So this is the question that is being asked. So I hope you had seen this kind of problems before. So without asking you to solve it, I'll just directly solve it. So what is the procedure? First, frequency is given to you. So here inductance is given. So inductance L is 20 millihenries. So first you find out the reactance of this particular inductor. So XL. So what is XL? XL is nothing but J omega L, or we can say J 2 pi F L. So why it is J omega L? Again, from basic differential equation of inductor, you can derive that the relation between current and voltage in inductor is achieved by this element XL. So let's substitute. We have all the values. We have J 2 pi and frequency is 50 and inductance is 20 millihenries. So into 20 into 10 power minus 3, like this. Now this is the calculation. So for calculation, let me use an octave interface. So let me just open my interface. Okay, so what you are seeing on your screen is an online MATLAB solver. So you can just go to octaveonline.net and you can do that. So I'll be entering my commands at the bottom. So let me begin by doing that. So here, so you can see at the bottom of your screen. So I'll write 2 into pi into frequency is 50 into inductance is 20 e to the power of minus 3. So this will give me the value of the inductance. Now on the screen you can see 6.2832. So that is the inductance. Similarly for capacitance also it is XC, that is nothing but 1 divided by 2 into pi into 50 into L. So into C. So that was 200 microfarads. So 200 E minus 6 I'll write. So I'm getting 15.9. So 16.3, I'll approximate this value to 6. So after doing these two calculations, now let me go back to my original screen. So here I have done this calculation. So I am getting the value J 6.3 ohms. Similarly, what is the value of XC? XC is nothing but 1 divided by J omega C. So this is nothing but 1 divided by J into omega is 2 into pi into 50 into capacitance is 200 micro. So 200 micro. So that means into 10 to the power of. So from all this calculation, just now I have done that. So this 1 by J is nothing but minus J. So J when going from denominator to numerator will become minus J, and then the impedance is 15.9 ohms. So like this I got the values. So let me redraw the circuit now. The circuit is like this. So the source is 100 volts and the phase angle of source can be assumed to be 0 degrees. Then I have a resistance, then I have an inductance, and then I have a capacitance. So these three elements are there which are connected in series. So basically it's the same circuit. And the resistance value was, let me refer to that. Yeah. So resistance value is 10 ohms. Reactance value XL I am getting is J 6.3 ohms. And the capacitance value XC I am getting minus J 15.9 ohms. So all these things are in ohms, but then I cannot join, I cannot add them because this is real number and this is imaginary number. So let me calculate now the final impedance. So total impedance is nothing but R plus XL plus XC. So I'm getting 10 plus J 6.3 plus minus of, that means so it will become minus J 15.9. So effectively, the positive component of this real number 10 will remain 10 as it is, but because this negative is more, so it will become minus J. And then what is this? So 9 minus 3 is 6 point, and then 15 minus 6 is 9. So 10 minus J 9.6 ohms is the impedance that I am getting, total impedance. So once you have the total impedance of the circuit, now I can find the current. So what is the current? Current is nothing but voltage divided by impedance, just a simple Ohm's law. So now what is the current? Current is nothing but voltage divided by total impedance. So that is nothing but 100 at an angle 0 degrees. So I can just simply take 100. So divided by 10 minus J 9.6. So this is an operation of involving complex numbers. So again, I need to use some kind of a calculator to do this calculation. So let me do this calculation. So I go back to my MATLAB screen and then I'll do that calculation. But electrical engineering we use J. So because in electrical engineering I is used for current, so not to confuse. And then the way in which we specify complex number in MATLAB is that the I will come after the number. So 10 minus 9.6 I is the proper way. So now if I press enter, so I am getting 5.2 plus 4.995 I, or I can just consider it as 5I. 4.995, I can round it off to 5. So 5.2 plus 5I is current. So let me go back to my main screen. So I have calculated the current completely. Now, but the problem is the current, whatever it is there, it is in the form of real and imaginary components, or rectangular form it is called. Now I want to convert the rectangular form into polar form. So how to do that? In fact, we should do that as the first part of this. But anyway, we'll do that in the next question. So how to convert a rectangular number into polar number? Amperes. So I should get this into polar form. So how to convert it to polar form? So a small diagram will help you. So think of a diagram like this. So on the horizontal axis, the current measurement is 5.2. That means here. So this is 5.2. So vertical axis is imaginary axis. On that I will mark 5. So corresponding to 5 on imaginary axis and 5.2 on the real axis, there is a point, and if I join that point with the origin, then that line, what we are calling is the current. So what is the length of this line? So simply using the right angle triangle principle, so the magnitude of IL, I can simply find that is 5.2 square plus 5 square and under root. So like this I can find the magnitude of I. Now not only that, this angle theta. So this is the angle theta I want to find out. So from this triangle I can find theta is nothing but tan inverse of the opposite by adjacent, that means 5 by 5.2. So like this also I can find the theta value. But there is a direct shortcut method of converting a rectangular number to polar number in MATLAB. So what is the command? Simply IL is nothing but absolute value of 5.2 plus J5. So this will give me the absolute value, and then the angle I will get simply by a function called angle of 5.2 plus J5. So this will give me angle. But the problem is this angle will be in radians. So you need to convert into degrees. So just multiply by 180 and divide by pi. So this will convert the radians into degrees. This is a conversion factor. So finally I'll get the angle in degrees. Okay, so let me show this how I do it in MATLAB. So I'm going to again MATLAB interface. Okay, so here this answer I'm storing in the quantity called capital I. So I'm getting capital I value is like this. Then I'm now interested in absolute value of I. So that is 7.2139. What you are able to see on the screen. So if I write the absolute value of I, the value it is calculating. Similarly, I want to calculate angle of I. So when I give the command angle of I, so that angle of I will be displayed in terms of radians. So we are getting 0.7499 radians. So in this radians I can convert into degrees. So how to convert into degrees? So as I said, just use the factor 180 by pi. So that is what I am going to write in the command prompt now. So angle of pi, that's what I'll have to type it. Then my answer will come. You can see 43.831 is the angle. So 43.8 degrees. So let me remember these numbers. 3.8. So let me go back to my screen. This is the final value of the current that we are able to find out. Okay, so now one thing still left out to do, that is we now need to draw the vector diagram. So let us first begin the vector diagram by drawing the supply voltage. So supply voltage is 100 volts at 0 degrees. V equal to 100. So now why this is 0 degrees is because I'm taking voltage as the reference value. So if this is there, then just now above I am calculating IL 7.2 amperes at 43.8 degrees. So roughly at the angle of 43.8 degrees, so I can draw the current like this. So this is the IL. So this is 43.8 degrees and the magnitude is 7.2. This angle is 43.8. Notice that the IL is leading wheel because the angle is positive, and so therefore it is above the voltage, that means the current is leading the voltage, and which is also expected because if you look at the impedance, the capacitance is more than the inductance, so overall it is like that. So this is the case. Now we need to also do one more thing, that we need to calculate the voltages of each component. So now if I draw the circuit once again, let me draw the circuit here. So I have a resistance, I have a reactance, and I have a capacitance. This total voltage supposed to be 100 volts. So what is this voltage? So this is 10, this is J 6.2, and then this is J 15.9. I think it is 6.3. So this is minus J6.1. Now we already calculated the current also in this. So the current value is 7.2 amperes and at an angle of 43.8 degrees. Now this current will flow in the resistance, there will be I into R drop. So 7.2 into 10 is actually 72 volts. And so let me draw that. So that what is the angle of that? Because the angle of 10 is 0 degrees. So 70 magnitudes you multiply, angles you add. So 7.2 multiplied by 10 will be 72, and then 43.8 plus 0 will be 43. So that way I can know the voltage across the resistance. So let me draw separately. So this is the overall voltage V equal to 100, and here 72 volts, I am getting something like this. This I am calling as VR. Then after that, this 72 into 6.3. So what is the voltage drop across the inductor? So VL is nothing but I into XL. So that is nothing but current is 7.2 angle 43 multiplied 43.8 degrees multiplied by impedance is J 6.3. Now what is J? J represents imaginary axis, or in other words J represents 90 degree shift. So 90 degrees it will be more. So what is 7.2 multiplied by 6.3? Let me just calculate that quickly. It is 45.3. So this time angle will be 90 plus 43.8. So I'll get 133.8 degrees. So in that angle I'll get the next vector. So that is this one. So this will be I into XL. Similar, and this angle is 90 degrees. Similarly, I'll get one more voltage, that is VC. IC into XC. So what is IC? IC is 7.2 amperes at an angle of 43.8 degrees. What is XC? 15.9 angle. Okay, this is 15.9 and this is multiplied by minus J, that is minus 90 degrees. So this one will be downwards. So what is the magnitude? So let me, okay, so thank you. So JNTU Kakinada already calculated the angle, so and the magnitude. So let's see. So 7.2 multiplied by 15.9. So I'm getting 114. So I think you need to please check. It is not 144. It is 114. So similarly, 90 minus 43.91. 831, 46 degrees. So the angle is correct. So 114 angle 46 degrees. So let me draw that. This is another vector. This is VC, or this is nothing but I into XC. This is VL, I into XC. So the addition of these three will again come back to 100 volts. So what you notice is V equal to VR plus VL plus VC. So this is the vector addition. These are all vectors. So far any doubts you have based on what I have discussed? So take a couple of minutes. If you have any doubts, feel free to ask. So let's call this example 14-2. Following 4 AC quantities are given. So that is, let's say, IA equal to 20 minus J7 amperes. IB equal to 5 plus J3 amperes. IC equal to 13.5 at an angle of 40 degrees amperes, and then Vs equal to 400 at an angle of 0 degrees. So determine first one is IA minus IB. Second one is IB plus IC. Third one is power supplied when Vs gives current of let's say output current of IA. So this is the question. So I'll give you 5 minutes time, and I request all of you to attempt this question and try to solve. So determine, and then you convert everything in polar form. Problem I showed on the screen. Please take 5 minutes time and try to solve this problem. Some of you have calculated the answers. So can someone give the answers for this? What is the value of first one? IA minus IB. So can anybody tell what is IA minus IB? Nobody can tell what is IA minus IB? So yeah, so JNTU KUCEV, they are saying it is 18.09 at angle minus 33.65. All right. What about IA minus IB in rectangular form? IA minus IB is 20 minus J7 minus 5 minus J3. So this minus will be multiplied for both minus 5 and minus J3. So this total will become 15 minus J10. So what is 15 minus J10? This we have to convert into polar form. So yeah, 15 minus J10. So how to convert to polar form? So again, let me use my Octave interface to convert this 15 minus. So here, let me quickly sign in. So on the left side, I can create a new file. So instead of individual commands, I want to create a small file. So I'll say AC quantities. So now if you look at your screen, on the left side, I write my program, and on the right side, I'll create the commands. So let me write the program. So here I am writing IA equal to 20 minus 7I. So this is IA. What is IB? So IB equal to 5 minus 3I. Sorry, 5 plus 3I. So this is IB. So what is, I am just entering the data. IC is 13. Okay, we'll come to that. So now I want IAB equal to IA plus IB. So now if I save and run, so on the right side, I'm sorry, IA minus IB we require. So if I now press the run button, so I'm getting 25. So I think I have to say it. So now you see 15 minus 10 is the correct answer. Let's calculate in the polar form. So how to calculate polar form? So IAB. So what I can do is I open a bracket and then say absolute value of IAB and then angle of IAB. And then this I multiply by 180 and divide by pi for converting into polar form. So now if I run this command, so save and then run. Yeah, I think the brackets is a problem. Okay, save and run. So here 18.028 angle minus 33.69. So yes, so the answer given by JNTU KCB is correct. So I am getting the same answer 18.028 and 33.69. Good. So let's do the second part, that is IB plus IC. Okay. So IB plus IC, again one institute has answered DMSSVHC, that is 9.83 minus 11.7J. So let us verify that. So how to calculate? So first I will define IC. So how to define IC? Look at the screen. So IC is nothing but the magnitude is 13.5. Then for angle, what you have to do, you say multiply and then exponent and then I into whatever angle. So angle was given 40 degrees. So 40 divided by 180 multiplied by pi. So like this we have to give. So you once again look at the third row. So IC is first magnitude multiplied by e to the power of I theta. So the theta should be in radians. So I converted into radian. Divide by 180 and multiply by pi. So now if I save, IC value is there. Now I want to calculate what is IB plus IC. So that is what is our second question, IB plus IC. So IBC equal to IB plus IC. So now let me save this program and run it. Yes, so I'm getting 15.3 and 11.7. Okay. So unfortunately, I think there's some problem with the answer. Answer given by DMSSVHC. It is not 9.83, it is 15.3 and angle is 11.7. So that imaginary component is correct and it should be minus. So I request once again to check that. Now what is the absolute value and angle? So I just copy this line and then change the variable. So IBC and then IBC also here. So now let me save and then run. So 19.28 and the angle is 37.2. So yes, the answer given by JNTU KUCEB is the correct answer. Okay. So let me, so far whatever I have done, let me record these answers and let's go to the last one. Power supplied by VS gives output current of IA. So So for that, first what you do is convert the IA into polar form. So how to convert IA into polar form? So again, I just copy this and then here I'll use IA. So IA is 21.2, angle is minus 19.3. So I'm getting IA like that. So let me record this answer. I'm going back to my main thing. So this is my MATLAB code. And what is the result I'm getting? So finally, I'm getting the answers. IA equal to 15J10, which is equal to 18 at 0.7 degrees. And similarly, this is IA minus IB. So this is IB plus IC equal to 15.3 plus J11.7, which is equal to 19.28 at an angle of 37.3 degrees. Now let's come to the third question. So the third question is something like source. The source is here, Vs. So this source is giving a current. So this is an AC source actually. So 100 angle 0 degrees. Is that what is the magnitude? Sorry, 400. And the current output here is nothing but the value of IA. And the value of IA is 21.2 amperes at an angle of minus 19.3 degrees. So this is IA. So now how to compute the complex power? So complex power is nothing but V into I conjugate. So this is an important formula for calculating the complex power. So now this is complex power. So what is the values now? So the values are S equal to 400 angle 0 degrees multiplied by 21.2 angle minus 19.3 degrees. But then I have to take the conjugate of this. So what is the conjugate of a polar number? The magnitude will remain same, just the angle will change. So that is nothing but 400 at an angle of 0 degrees multiplied by 21.2 at an angle of 19.3 degrees, like this. So now this is nothing but 400 into 21.2. So it's just a simple calculation, 400 into 21.2. So I'll get 8480. 8480 at an angle of 19.3 volt amperes. So this is the S. Now this number I can convert into rectangular form. So when you convert that into rectangular form, so how to convert that? Simply you take the number and then just convert by the formula. So this is nothing but 8480 e to the power of j into 19.3. This should be converted to radians. So into pi by 180. So this one you will get it. So this you will get 8003 plus j 2802 volt ampere. So what is the meaning? Therefore, the source is supplying 8003 watts of active power and then 2802 watts of reactive power. So this is the source is supplying both kinds of power, active power and reactive power. So I hope we had solved this problem. So I hope you understood something from this. So you have any doubts in this problem? So before I close the class, so just there is one doubt which is being asked. So let me paste the doubt here. So element energy stored. So this doubt is asked by JNTUK. So element is inductor. So inductor stores the energy in what form? So electromagnetic field. So another is capacitor. So energy stored. So it is electrostatic field. Now the question is resistor. What form is the resistor storing the energy? So this is the question. So the answer is resistor does not store energy. Any energy given to is converted to heat energy and lost. So this is the answer to the doubt. So based on this, there is one more. Let me give you a homework. Apart from resistor, inductor and capacitor, another fundamental element has been invented. So this memristor has been invented in 1971. That element is called memristor. Symbol. This is a symbol for that particular memristor. So homework is find out more about that. So find out more about memristor. So I think we are anyway end of the time. So if you have any questions about this lesson, feel free to ask the questions, in the next class. So I think we'll conclude today's class here and see you in the next week for the next lecture. Thank you.